everyone. It is my pleasure to introduce Dr. Nadine Hoffmann, who is our speaker of today. Nadine is a postdoctoral research assistant at the Marine Geoarchaeology and Micropaleontology Lab at our Department of Marine Geosciences, working on research on tsunamis in the Eastern Mediterranean. Nadine completed her PhD at the Tectonics and Natural Hazards Group at RWTH Aachen University on the tectonic evolution of Reef Basin, Macedonia, Albania, and did her research and teaching training at Tectonic and Natural Hazard Group at RWTH Aachen University with focus on risk assessment of natural hazards. Please,
thank you. Okay, thank you for having me here, giving me last talk of the semester. I want to give you an overview of what we are doing at the lab currently, and I want to talk you into Palaeotsunami evidence and the southern Israeli coast. Palaeotsunami means basically everything that has been sedimented and we can still trace it in the sediment record. So general, when you think about tsunamis, you think about those pictures. That's 2004 Indian Ocean tsunami. That was an event from the earthquake at Sumatra. It was a 9.1 magnitude earthquake, and we had a wave approximately up to 20 meters run-up height. So this is at least the records we get from different sources. That's a picture from NASA. That's basically a before and after picture, a couple of days before and after the event. If you look at the coastline and the red squares especially, you can see what damage the tsunami did in certain regions. So it really affected the coastlines and also had an effect inland quite a bit of the area. Another example everyone has in mind is the 2011 Japan tsunami. So we're talking about the big shots here. This is another 9.0 magnitude earthquake, run-up heights probably around 15 meters elevation. So also a really big thing. The nice thing about, but the interesting thing about the Japan tsunami was because of the early warning system, we have those amazing pictures from people standing on elevated points and looking at the wave coming in like you can see it here. So we think about tsunamis and we in general think about those events happening in the Pacific area. So basically what you can see here is the number of events circling around the Pacific plate, and the dots give you the earthquake-induced tsunamis, and the triangles are events triggered by volcanic eruptions. And there's a couple of other events hidden where the source is not quite clear, but actually this is what we think of tsunamis, like when we think about them, it's more or less in this area. But you might also notice that there's another, well, let's call it hotspot, which is around here. And you probably know this area because that's the Mediterranean, and this is where we want to focus our research on. This is what the people ask me if I'm telling them what I'm doing and what I'm working on. But the Mediterranean, come on, tsunamis, really? The thing is that the tsunami basically, theoretically at least, can happen in any water body. So if you want to break it down, even in lakes. The only thing that you have to think about is, we need a source of the tsunami. When it comes to the Mediterranean, I just want to throw out some dates there, because you might think, well, it has been in whatever, medieval times, I don't care about it. But actually there's a couple of recent ones. I don't want you to read all of this, but there has been a quite recent tsunami in 2003, just a little one. It was probably really small waves, probably around a meter or something. It was hitting a port, destroying some ships, nothing really big, but 2003 is quite recent, and it has been in the Mediterranean. There's a couple of other ones. I also want to draw your attention to the 1755 Lisbon earthquake. You probably heard about that. It's one of the big earthquake events. And also there we had a tsunami that hit the Madeira Islands. Run-up heights up to 50 meters based on eyewitnesses. So yeah, just for you to kind of think about it. So what are the possible sources? Earthquakes, you heard about that. Volcanoes, we were talking about that as well. Landslides. Landslides are accounting more for more localized events, whereas earthquakes and volcanoes are more regional, normally cause more regional tsunami events. And you might have heard about meteorites. Not so often, but can happen. And there can be anthropogenic sources. So deep sea mining, for example, explosions, whatever there is. If you talk about earthquakes, this is a pretty complicated chart, and I want to walk you through that a little bit. The thing is, we're not talking about magnitudes here, we're talking about intensity scales. Earthquakes are characterized not only by their magnitude, which is the energy released, but also by their intensity, which is basically the shaking intensity, which is often measured by different occurrence of different phenomena, but also by people reporting certain intensities in a certain area. Intensities also don't describe a large lateral spreading, but really the intensity in a certain area. This has been developed by Michetti et al. And tries to first it's the first chart that tries to sum up in certain intensity level with certain occurrences of geomorphological changes during an earthquake. So what is interesting for us is everything above intensity 8, and this is what we talk about now. Intensity 8 is something around magnitude 6. It depends a little. It can be a little bit higher than magnitude 6 and still have an intensity 8. I think it starts around 5.8. That is like the lowest magnitude that can produce an intensity 8 level. But if you look at it, like we get offsets in the centimeter range, decimeter range up here, and we also can produce already waves. So we're not necessarily talking about tsunami waves yet, but we can have waves, either standing waves or already like the beginning of tsunami waves. And if you go up in the intensities, and up here we're talking about magnitudes 8 and more, then we also talk about those giant tsunami waves, 10 meters and more. So let's go back to the Eastern Mediterranean. What are the tsunamigenic zones? So for us, we have to think about when something happens, when an event happens, how can it travel to the Israeli coast, and would it affect us or not? So for us, the most important sources are Cyprus down here, then we have the Hellenic Arc and Crete down here in that area. The Peloponnese, which is supposed to be a really high risk, is probably not affecting the Israeli coast because of all the islands, and it probably is not going down so far that it could be interesting for us. Sicily is an interesting source, although it's quite far away already. And then we're talking here in this area about the Lebanon Truss. So these are basically the tsunamigenic zones which are interesting for us. So now we look into the historical earthquake records. This is, I'm sorry for the quality, this is a really old book from the 1920s. It's also a German book, so also the spelling of the names might be a bit weird. But interesting enough that even in the 1920s they already had an idea, and they produced something that pretty much looks like intensity maps. And I want to show you this earthquake, which they call the Galilee earthquake of 1202, because this is something that also we see later, and I'm going to show you in our records that this age also kind of pops up every now and then. So, but you can see that also here there's a couple of earthquakes that are from the Levant that have been reported already so early, where the research has not been so, let's put it so advanced than we're talking right now. If it comes to volcanoes, there's not so much around that still is big enough and active so that we should take it in consideration. But we should at least talk about Stromboli and Etna, and then there's a couple of Greek volcanoes. Here is the Santorini, Misiros, Milos, which are still also considered active volcanoes. So for volcanic sources, these ones should be at least in our minds. And there's landslides. As I said before, landslides are creating a more localized tsunami event rather than those big events we get with the large earthquakes. For us, interesting is especially the Nile Delta, because with the buildup of so much sediment, of course, it is prone to, or the risk of a slipping event in the Nile Delta is relatively high, and it's still close enough to maybe affect the Israeli coast. Another big thing is the Israeli slum complex, right in front of Ashdod. Here's Gaza City. This is just a map of how the headscarp looks like. But if you're talking about the southern Israeli coast, of course, this might also be a source for tsunamis. Imagine this slide just goes off in one event, how much energy it will release and how much water it will actually be able to move. So the Israeli coastline. If you look at the Israeli coastline in general, it's relatively flat in most areas. So this is a picture from the Tsunami River looking to the north. There's not much elevation changes really, and also this is a picture, I think, from Olga looking to the south. Also the cliffs, I mean, we have cliffs here, but they're not like 30, 40 meters high. They're more like 5 meters, maybe 10 meters, so this is what we're dealing with. On the right-hand side, and this is just a really crude thing I just made a couple of days ago, it's an image of SRTM data, and I just gave different elevations. So what you see here in red and orange is anything up to 5 meters. So anything that is more or less lower than 10 meters, and if you imagine a wave that comes in 5 or 10 meters, what would happen? And if you look here in the Haifa area, it's quite far. It doesn't look so bad down south, but imagine that this is the whole northern coast of Israel. So it's also intriguing a little bit that you really, if you zoom up in the areas, you see that actually in some areas the rate would run up really, really wide into the country. Just a simulation, just to have an idea what the vulnerability is in these areas. There also has been some modeling done. What would happen if a tsunami, if an earthquake, for example, in Cyprus, creates a tsunami wave, and we're talking about 1.5, 1.4 meters. It's a simulation. It's nothing where you can really say, okay, this is the real data, and we don't have any proof. Like we were just discussing it before, we don't really have any proof and say, okay, yeah, if a tsunami hits, it's gonna be that far up or that long, that much inundation inland or something like that. We don't really have that data, but this is an idea. And if I go back to that picture and you just look at the red areas, this is everything below 5 meters. So you see that this 1.5, 2 meters wave heights could affect still those areas, and that's still a lot. So when we're looking at events now, that's a compilation that's been done by Solomon et al., and they tried to put in all possible reported tsunami data from historical sources, whatever there was, and try to figure out what kind of already hit the coast, or what was reported along the coastline of Israel. And there's a couple of dates we've been seeing before, which is here again, the 1202 we've been talking about before, coming from up here. And I don't see it right now, but there's also, oh, maybe it's on the next slide. Yeah, here. There's also the 365 tsunami that has been, was an earthquake in Crete that also has been reported from Alexandria in historical records, and it also probably has been hit the Israeli coast. On the right-hand side, I just compiled a couple of data you can find in the literature. So this stuff has been published. There's a 1500 BC tsunami, which kind of fits with the Santorini eruption. There's a 115 AD, 551 AD, and 1759 AD tsunami that have been proven. And there's a couple of historical records, like the 365, the one that has been reported from Alexandria, for example. So this is just what's relevant for the Israeli coast. Everything else, there's of course, when you talk about the Eastern Mediterranean, there's a couple more, but this is pretty much what might be relevant for us. So let's talk about the project. I was involved in the very beginning of the project, but there were a couple of bright minds that figured out that they want to know the tsunami evidence from the whole Israeli coastline. And they started to go off drilling cores from the shallow shelf. And I don't know exactly the number of the cores, but it's exceeding 10 or 12 or something like that. So it's quite a bunch. And basically it goes up as far as Aceh, and the southernmost point would be Ashkelon, and this is the transect I'm talking about today and showing you some data from. So, but why are we going offshore? It seems to be so much easier to just stay on land, throw your equipment out there, get a couple of cores, collect some onshore samples. Actually, yeah, but there has been a study from Straczynski et al. From the Indian Ocean tsunami, and he's been working in Thailand after 2004. And he figured out that only 50% of the tsunami deposits have been preserved after 4 years. 4 years. And we're looking on stuff that's a couple of 100 years old. So he figured out that 30% has been removed by human activity. So people are cleaning up. People are going there and build houses, remove the trash, whatever. And 20% of the tsunami deposits were eroded, or due to soil formation, they were not recognizable anymore. So I want to show you some pictures. The upper sequence is showing an area in February 2005, right of, like, you can see the tsunami deposits really well. In 2006, 1 year later, you already see that people cleaned up, like all that garbage has gone away, the vegetation starts growing again, you don't really see anything anymore right meeting the eye. From a personal report of Vital that did the photographs, he said in 2007 he wasn't even able to take the photograph from the place anymore. He used to take the pictures because it was all overgrown, like there were bushes and trees and whatever, so he couldn't even get in there. So this is, I mean, it's the tropics. It's nothing we can compare with the Mediterranean, but it's interesting to see how quickly those things changes. The bottom sequence shows us, it's probably not really good to see, but there's a 2 centimeter tsunami layer on top, which he shows here. Another year later, the topsoil has just been removed, nothing left. Probably because of soil building, probably because of animals burrowing in there, probably because of rain washing things away, things like that, but gone, nothing there anymore. So he said, or that's what came out of the whole study, he said, like, when we're building a tsunami deposit on top of, like, the black one is the old soil, the yellow one is the tsunami deposit on top of the soil, and due to heavy rains in the winter season, due to bioturbation by animals, by roots, by whatever, a lot of the material is already removed. So you can see here on the highs, for example, there's not much, or if there's even something less left. After a couple of years, of course, more soil builds up, and there's also a mixture due to soil building. And what's preserved of the tsunami we can just find in those lows, maybe. Or if they're more like channels, it could also be washed out. But it's not so much preserved as we would think of. So that kind of gives us an impression what happens on land. And our idea is basically that if we go offshore in the shallow shelf, there's no one cleaning up. There's not so many animals making holes in the ground and things like that. There's not so many plants. So we're hoping that the preservation is better in this offshore scenarios. So that's what we do. We go on the boat. That's our fieldwork. That was the 2013 expedition on the Medex. And what we use is it's a diver-driven pneumatic hammer that drives the core into the ground. I think our deepest core, as far as I remember, no, not the deepest core, the longest core was around 4 or 5 meters. And of course, because it's diver operated, we are limited to about maximum 50 meters water depth. So we're really operating normally between 10 and 30 meters water depth. And then we go into the lab work. So the cores come in aluminium liners, which we need because of the hammering of the device. Every plastic liner would just splinter. It has some problems because we cannot use certain techniques anymore. I was trying to run magnetic susceptibility later on the material. It just didn't work because it was stuck in an aluminium liner before. But on the other hand, the retrieval in this technique is a lot better. So we opened the core with a disc saw, heavy work. And then if it's already sliced in half, we kind of try to open the halves really, really careful that nothing falls out or we don't disturb the sediments too much. And the whole lab is present, of course, looking at what great things we found there. It's always really, really exciting if the thing, it's like Easter, everything opens up. And then comes the sampling part. So what I do is I first of all just describe and photograph the core, of course, and then we sample every centimeter. Take samples and describe it all the way through and look what we can find on the way already. And this is how it looks like. That's the core afterwards, the full box of dirt, more or less. This core was amazing because when we opened it, it was just popping into your eyes that there's something happening. So this was just a 1.10 meter core, and we didn't. It was coming in one piece. We didn't slice it or anything. And what meets the eye is that there's pretty nice. I can tell you it's sand, pretty nice sorted sand, and then those areas here. And this is what it looks in a close-up. This is pretty much the background we get, and then suddenly we have those really coarse material, lots of shells and stuff like that. I don't want to interpret it now, but if you look at it a little bit again closer, this is a really nice, well-sorted sand. Quartz grains, not much not much shells or anything in there, and this is what we call the background sedimentation. And then we get those things. Oops. Then we get those things. Get coarser grains, shattered shells, pieces of wood, whatever, name it, you can find it. And Beverly actually came up with the word tsunami because we need to classify it somehow. We don't really want to say it's a tsunami layer already, but it kind of looks like tsunami-ish, so we stick to the word tsunami. So where comes the background sedimentation from? Not a literal cell. I think that's something I don't really have to explain, but the Nile Delta is transporting all the nice fine-grained sands up to the north, and we're somewhere around here. So this is basically the background sedimentation what we get. And the nice thing about it is it gives us almost textbook-like differences, because this is really well recognized, really well, as I said, really well sorted, and whatever changes there happen, you can see pretty nicely. So what's next? Grain size analysis. We're sitting in the lab, putting everything through the grain sizer. So we are looking at grain sizes up to 2,000 microns, and what we try to see if there's any differences happening that are obviously to the eye. So when we're talking about the Ashkelon site, we have those three cores. It's a transect of 3 different depths. So we have approximately 10, 20, and 30 meters water depth. And a nice thing about the transect is that we think if a tsunami sediment is preserved, it will change over with depth. So the material will become finer, and the tsunami layer itself will thin towards the sea. Like if you go deeper, it will thin out. And that will also help us to detect the differences between tsunami and flat sediments. So, or large storm surges, things like that. Because that's what we want to rule out. We want to be sure it's not a storm, it's a tsunami layer. So this was the deeper core we got, and as you can see, you can't see a lot on the first site. Of course, there are some areas that are a bit darker, and some areas that are a bit not so dark, and you get some shells, but it's nothing really so obvious. This is how the core looked like when we just opened it in the field. Same thing. You can see something lighter material here. There's a little bit more higher water content, but that's pretty much. I mean, you cannot really say, well, that's a great tsunami layer or anything like that. So let's do the homework. This is basically what it looks like after the grain size. It's particle distribution contour map. We use the ODV software to calculate it, and what you can see is the grain size distribution of them. The numbers didn't come out, but it's basically particle size from 0 to 2,000. This is just the depth of the core, and it gives you percentages. So the color code gives you the darker it gets, the higher percentage of a certain grain size you have in this area. And what you see is that in some areas you suddenly have those not really nice sorted materials with a high amount of bigger grains. And I cannot say a lot about this because I just got this 2 weeks ago, so the interpretation has not been done. I just wanted to show how it looked like. And the 3 big circles are actually the places where we've also found datables. So this is what we sent for dating, and hopefully get out some nice dates that might fit to something. But I picked the dates according to what it looked like in the grain size, in the particle size distribution. So what we're looking for is not really well sorted stuff. So if you see here, it's like you have a lot of really large grains and medium size, but also a couple of smaller ones. So it's kind of not really nicely distributed. That's the shallow core, the one you already saw before. And that's a close-up of the lower, let's call it again, Tsunami. And what you see on top, there's a relatively sharp change from the coarse material to the again nicely sorted sands. Whereas on the bottom, you also still have like a couple of shells. It's not so nicely distributed. But we're talking about pretty much 10 centimeters. So this is first a high energy event we're interested in. If you look closer, what's in there? It's a lot of broken shells. Unfortunately we didn't find any pottery or anything like that, but we had other cores from Caesarea, for example, where we really had pottery shards. But you get seeds, you get charcoals, you get a lot like little like pebbles, unrounded pebbles, a really mixture of different types of things. We also found imbricated shells, and they are really nicely. So they are really lying like on top of each other. We couldn't preserve it as it was, but I tried to take as many pictures as I could just to be able to trace that later. And this is how the contour map looks for this core. So of course, think that you have to keep in mind that this is just a fourth of the other core you just saw. So of course the picture looks a little bit different. But what you can see here also is those two really distinctive layers. I'm just in a minute I'm talk about this as well because this is a bit problematic. But you see that this fits quite nicely with the actual tsunami layer we had here. So you also get those not really well sorted sands and a lot of a high percentage of coarser grains. Whereas up here you get those really nicely sorted sands. Of course, yeah, there's some outliers which we're still not sure what to make out of it, and you get those little peaks here, which we think might be storm deposits. So, and the interesting thing is also, if you would go back to the other core, you don't find them there anymore, at least not so distinct. The thing down here is a bit problematic because of when we opened the core catcher is made out of brass, and we found a lot of concretions next to the brass. So, and you also see that the color changes here a little bit in the bottom. So I don't want to take this signal here too serious because it could just be that the concretions are not just really close or really big, but also in a smaller scale and gives us bigger particles that maybe are problematic. So we didn't pull out dates here, so we might date this area as well, but it's just something you have to be careful about. So it's always good to go back to your notebooks and look at the things you saw and also write down those things because alterations might just, in this case, might just give you a signal that's not really there. So what's next? Dating. We try to date articulated bivalves. That's our main purpose. The reason is, I show you, here's one that's still sitting in the sediment, that's still attached in the top. I don't know the scientific name for it, but it's still together on the top. This also is still together, and this is the same specimen, but just cleaned and sent off for dating. The reason is the shells are held together when they are living by a band. As soon as they die, they would fall apart. So it means when they're still together in a sediment where we find them, that they actually died there. And this is what we want to have. So if we have a high energy event and we found those articulated bivalves within the sediment, we know that even after that they haven't been transported a long time. They have been deposited alive and died there. So it gives us a pretty precise date on the layers we are looking at. So I hope you can see it. This is again the whole core ETC1, the more shallow one, and we try to date, of course, within or above tsunami layers. And the first date we pulled out was 1149 to 1223 AD. And if you kind of remember, we had this date before 1202 tsunami, so it kind of, could work. Of course, that's not, it's not set in marble yet. It's not something it's just something you can throw out and think about, and maybe it fits together. There's another couple of dates, and I go back to those dates later to show you what what we made out of it. So this is our final conclusion. Remember this chart where gave you some ideas of what kind of tsunamis happen to the coastline, and the red ones are the date we pulled out of here. There's one missing, which I put here because it's way out of anything that we have any record of. But if you look at this, there's two big events, which is 1202 and 1222, and this date actually would fit in this timing. There's another one, the second one, which is within this huge layer you saw before, which is also around the 551. It's not exactly fitting, but we still have to see what we make out of that. Also, this huge layer is kind of still giving us riddles. And then we have this 365 Crete earthquake, Crete tsunami, with also a date that kind of fits at least in the range. So preliminary conclusions, pretty much what we've done up to now. A couple more things are on the way, so we want to look at the foraminifera assemblage to see if there has been any change in the foraminifera. That's a lot of work that we're still going to do. There is another core we're going to open, so we'll see what that brings. And then we also have to think about those signals we haven't been really be able to date yet, or figure out what exactly they're telling us. Yeah, thank you.
Thank you very much. Any questions, please? Okay, so I have a question.
Yeah.
So probably I didn't understand. Do you have any indication about the intensity?
No. No.
And another question. So if you have an earthquake, can you separate tsunami and earthquake in the sediments?
First of all, not every earthquake creates a tsunami. So, and especially the earthquakes we are talking about are normally relatively remote. So we're talking about an earthquake happening in Crete that triggers a tsunami that comes towards the Israeli coast and hits the coast. So we don't see any evidence for the earthquake on the Israeli coast because it actually has nothing to do with it. But we can find the tsunami evidence. There's other earthquake phenomena that, for example, liquefaction. So when the ground shakes and the sediment has a high water content, there's those structures that look like flames. So the soil really liquefies and moves, but that has nothing to do with tsunamis. So it's just an earthquake. An earthquake-triggered phenomena which we can see on the coast most of the time, but it doesn't go together with tsunamis.
Okay, thank you.
Okay.
Any questions?
Any more questions?
Yeah, please.
How do you know if it's a tsunami or a landslide? Because as you said, it's a lot of landslides in this area,
Yeah.
with the IC complex and everything.
Well, especially in Ashkelon, we need to be aware of this landslide, the occurrence of landslides. What we try is that we link whatever dates we have, as I tried here, with historical records, because this strip of land has been inhabited since, 6,000 years, 8,000 years. We have quite a good record of when something catastrophic happened. The landslide phenomenon is a lot more local. So if we have a landslide in Ashkelon, it doesn't necessarily affect Tel Aviv area. So if we have, not necessarily, might be, but it probably doesn't go up as far as Akko. No one would see that in Akko. So what we try is, if you find a strong signal of a tsunami evidence in Ashkelon, let's say, and we still find it, for example, in Jaffa, then we can say it's a more localized phenomena. Whereas if we find it all along the coast, and this is what we try later, like to correlate all those cores, then it's probably something large, regional, and not just a local phenomenon.
Okay.
And the thing is, with the landslides, it hasn't been dated yet. I didn't find any dating on the Ashkelon landslide yet.
People are working on that.
I know. But there's not even
There's something else
preliminary.
that you have to remember. We're talking about the really shallow shelf.
Yeah, recent landslides.
There is no
Small.
landslides on a
No,
this is what we were coring, an area that is almost horizontal, sub-horizontal.
No, of course, but if a landslide
The
happens,
landslide happens on the continental,
It might generate, I mean, you're right, you only need about 2 degrees under sea,
I know, but
Under
it's
sea for a
just,
landslide.
I mean,
and it might generate a bit to the east and get that.
we're really
the
close to
question
the coast.
Yeah, I
It's
know.
really
So
on
that's
the
what
coast.
the next question was. If you, when you think about tsunami in this region, the tsunami will come from the west, and the landslide will come from the east, which are different sediments. So maybe this is how you can put this.
Yeah.
You can distinguish between them by the type of sediments.
it probably brings the same sediments, I guess.
I don't know, because if it comes from the deep, the tsunami comes from the deep sea, it brings everything basically, and a landslide brings maybe.
The question is, it's so much
These depths,
difference to actually be able to distinguish it. We have to look in that. Like, if we really see something that we think it's landslide related, we really have to look into the sediments. Maybe even go into like chemical analysis or petrographical analysis of the sediments and see if there is differences.
Seismic
Yeah.
also.
Yeah, that's.
This is where I come from.
The problem with the seismics is that it's, or also we were thinking about going into strata box. It's too shallow to do anything properly. So no data there yet. And I think the seismics are, I think they're 3 kilometers away from the core, like towards the sea. That's where the seismic starts. And yeah, as long as we don't have any dating from the landslides.
Okay. Okay, thank you very much, Nadine.
Thank you.
Ja.